this video, we're going to talk about sequential circuits, how to derive the Boolean expressions from a given state table using a computer design tool called LogicAid. In this video, it is assumed that the viewer has knowledge of what a sequential circuit and a state table and a state diagram are. This video does not go into those details. What it does is to explain how to take a given state table and derive the corresponding Boolean expressions that would allow a circuit designer to build the corresponding sequential circuit. A little bit of background first. There are two types of sequential circuits: a milli type of sequential circuit and a Moore type of sequential circuit. The main difference between the two are, in a milli sequential circuit, the external outputs, in this case there's only one, can depend on the value of the external input, x in this case. So in this example, when the present state is C, the output can be different depending on what the external input value is. On the other hand, in a Moore type of sequential circuit, the output, in this case there's only one, has no dependence on the external inputs. Hence, you can think of having all these columns collapsing into a single one because there is no dependence on the external input x. That means that the output z, in this case, depends only on your current state, whether it's A, B, C, or D. Therefore, there's no dependence. Let's take that example of the milli sequential circuit first. In LogicAid, we can create that state table. Input state table. It asks number of next state columns. In this case, there are two next state columns. One for x equal to 0, one for x equal to 1. Number of input variables. That refers to how many external inputs the circuit has. In this case, 1. Number of output variables. In this case, 1. Length of state names. This is just the number of characters that will be used to name each state. In this case, the names are A, B, C, D. These are the names of the states. Therefore, we only need one character, but we can just put a 2 here or anything more than 1. We are going to enter our own names so that we can name our own variables x and z for the inputs and outputs. And this is important. Since we're using a milli state machine, we need to have the corresponding tick here for milli. Press OK. It asks you to name your input variables. We wanted our input to match what we have, x, and the output is z. Press OK. And this is the entry for the state table. So this is pretty much a text editor. We can just copy what we have from the state table into the state table here in LogicAid. First row is A. Use the tab key. You can move between the fields. Next state is A for x equal to 0. Next state is here B under x equal to 1. And the output are 0 when x equal to 0 and 0 when x equal to 1. That completes the first row. So at this point, once you understand the format, it very much matches what your state table, what it looks like. Second row B, present state. Next states are A and C. Outputs are 0 and 0. You can use the tab key to move between fields or use the space. It doesn't matter. This is a text editor. Last row C. next states are A and C, and the outputs are 0 and 1. This completes the entry of the state table. The next step is to derive the Boolean expressions. First, we want to do a state assignment. Otherwise, it uses a default one. So a state assignment, what we do is we tell it how many variables we need, how many flip-flops or how many bits we're going to use. We have 3 states, so we're going to need minimum of 2 variables or 2 bits. We're going to enter our own names. These are the names of the flip-flops. And so we can name them Q1 and Q2. We could have used the default ones, capital Q1 and capital Q2. But you can change the names if you want to Q sub A, Q sub B to conform with other standards or nomenclatures. Press OK. And you can change the state assignment. Currently, it assigns A to 0, 0, state B to the code 0, 1, state C to 1, 0. This is the default. And if you didn't make a state assignment, this is what it would have used. You can change it to some other state assignments if you wish. But for the purpose of this demonstration here, we're just going to use the default and the standard one. The last step is to derive the Boolean expressions. Now, we're going to skip the state reduction, but if you're asked, and then oftentimes you may want to reduce your state table to make your circuit simpler, to derive simpler Boolean expressions. We don't need to in this example. The last step is to derive the flip-flop equations. We want the D flip-flop type. Press OK, and just use the default values. It is fine. Alphanumeric, sum of product forms, and just one redundant solution. Press OK, and here we have the Boolean expressions for the first flip-flop, the second flip-flop input, and the external output Z. With those 3 expressions, the designer can build the corresponding sequential circuit to realize the functionality described in this state table and in this state diagram. One can also derive very quickly the expressions for using JK flip-flops. Use all the default values, and here they have. These are the JK flip-flop equations for the first flip-flop, the JK flip-flop equation for the second flip-flop, and the equation for the external output Z. Lastly, we can also derive the flip-flop equations for a T flip-flop. Use all the default values, and there you have it. So with these 3 sets of Boolean functions, whether it's for a D type of flip-flop, a JK type of flip-flop, or a T type of flip-flop, a designer can take these Boolean functions and build the circuit. Now, the other part of it is, if we have a more type of sequential circuit, which for the most part, most of us will design, the process is very similar with just one caveat, one difference. So we start with input, Boolean state table. Once again, the number of next state columns is 2 because we have one for x equal to 0 and another set for next x equal to 1. So it's 2. We have one external input, one external output. Again, how many characters do you want to use for the state names? We're going to just write 2 here. We want to enter our own names. In this example, second example, we have a more type of machine, a sequential circuit, a more. Therefore, we select that, press OK, name the input. Our input is named X, and output is Z. These variables, they are just simply names. They're just characters, but you want to conform to your design so that everything matches and it makes sense when you look at the final Boolean equations. Once again, we have the same entry here, but the only difference is that on the output side, there is no 0 and 1 as in the previous example, because once again, in a more type of sequential circuit, the output does not depend on the external input X. It only depends on the state. So you don't see the dependence there. So we go and fill this out. First row is A, B, and the output is just a zero value, a single value there. Second row, B, next states are A and C, output is zero. Third row, C, A, D, output is zero. Next row, D, next states are A and D, and the output is 1. That completes the entry. So there is really no difference, but it's just understanding the difference between a milli and a more type of sequential circuit and how it is different when you enter that in your state table in LogicAid. Next step, we can do again the state assignment. 2 flip-flops. We're going to want to enter our own names. We want to name them Q1, Q2, so they're default values. That's good. We can change the state assignments, but we are going to use the default. State A gets assigned 0, 0, state B 0, 1, state C is 1, 0, and state D is 1, 1. Once again, we can now find the flip-flop Boolean expression for a D type of flip-flop. Use the default values here, and there they are. And we can also derive, go back to this window, routine flip-flop equations, JK flip-flop, okay. Derive them, right here they are. And go back to this window, routine flip-flop equations, T, okay. And there you have it, the 3 set of equations that would allow a designer to build this the corresponding sequential circuit, whether it's using D flip-flops, JK flip-flops, or T flip-flops. So this is the end of this video. I hope this helps you.